Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. Today I'll be discussing how to analyze the shear force and bending moment for a cantilever beam when it is subjected to uniformly distributed load throughout the entire span. So here in the sketch you can just observe that we have taken a cantilever beam of A as fixed end, B as free end, and it is carrying a uniformly distributed load of W per unit length over the entire length of the cantilever beam. So I have taken a section here. Which is XX, which is XX section, which is at the distance of small x from the free end, that is from B. So now if I want to consider, or if I want to find out the shear force and bending moment, so I just take, let Fx is the shear force at x, and then mx is the bending moment at x. So I just consider Fx is the shear force at x and mx is the bending moment at x. Now here we have considered the right portion of the section, and the shear force at the section x will be equal to the resultant force which is acting at the right portion of the section, but the resultant of the force is at the right side of the portion is equal to W into length of the right side portion. Means if I want to find out shear force at section XX, so that is nothing but if I want to find out from the right hand side, that is from B point, so it is nothing but the load which is acting here, that is W is the magnitude of the load which is acting. So for the length of X, so it is nothing but W into X. So shear force for a uniformly distributed load is nothing but product of the magnitude of the load into the distance to which it is acting. So therefore W is the magnitude of the load, x is the distance from B end to the top of the section XX. So therefore shear force at XX is nothing but W into X. Or you can also just interpret this as since W is in terms of load per meter, or so if at all if it is in terms of Newton, so it is in terms of Newton per meter, say suppose. So X is in terms of meters, so meters and meter get cancels and only the thing left here is in kilonewton. So therefore the shear force we have bought it in terms of the point load terms, that is kilonewton or Newton, like that. So always while finding the shear force, as in case of the uniformly distributed load, at any point we are supposed to take the load, magnitude of the load multiplied with the distance to which it is acting. So since the load into perpendicular distance, since it is acting in the downward direction, so here we are considering from right hand side. So as per our sign convention, right hand side downward direction force is considered to be as positive. So therefore W into X is the positive variation. Now if I want to find out the shear force at different points, so that is point B and point A. So shear force at point B, so that is nothing but, so here the value of the x exactly at point B, the value of x is equal to 0. So therefore if I just substitute in this equation the shear force at B, it is equal to W into 0. So here x is equal to 0. So therefore shear force at B is equal to 0. Similarly shear force at A, so shear force at A, here the value of x will be equal to L. The value of x at A will be equal to L. So therefore X is equal to L. W into L is the value of the shear force at A. So therefore these are the shear force calculation at the different points, that is B, X and A. Now coming on to the calculation of the bending moment. So if I want to calculate the bending moment at the section XX, so it is mentioned that the uniformly distributed load over the section is converted into the point load acting at the CG of the section. So bending moment at the section XX. So suppose mx is equal to total load on right portion. Why it is right side portion? Because we are going to take from the right side as a reference multiplied with the distance of CG of right portion, from X. So from X. So here the total load on the right hand side portion from that is of XX from that of B, it is nothing but W into X. So that is nothing but the point load, and the distance of CG from the right hand side portion. So from the right hand side portion, the distance of CG here is since it is a uniformly distributed load, always the CG will be exactly the half the distance. So it is nothing but the distance here is X. So half of the distance is nothing but X by 2. So therefore this is the value of the moment exactly acting at the section X from that of B. So that is load into the CG point. As in case of UDL, whenever the beam is exposed to the uniformly distributed load, in order to calculate the bending moment, we are supposed to take the product of magnitude of the load multiplied by the CG from the reference point. So this is the concept. Since it is acting in the clockwise direction, so right side clockwise we have considered it as negative variation. So it is taken as minus Wx into x by 2. That is nothing but Wx square divided by 2. So after getting the value of the bending moment, so here at xx, so we are supposed to find out what are the bending moment for the other 2 points, that is point B and point C. So moment at B is nothing but since the value of the x at B is 0, so therefore W into 0 square divided by 2, it is equal to 0 itself. Similarly at A, x is equal to L. So therefore it will be minus WL square divided by 2. So this is the value of the bending moment at point A, B and X. So drawing the bending moment and shear force diagram, first I will draw the baseline. First I will draw the baseline, and then exactly at point B I have got it as 0, the shear force, and exactly at point XX I have got it as plus Wx, and on point A I have got it as W into L. So since it is the uniformly distributed load, the variation of the bending moment is the variation of shear force is linear variation, hence it is joined by the straight line. So next is the bending moment diagram. So draw the baseline. So here the bending moment at B it is 0, at A it is WL square by 2 with a negative variation, so I have drawn below the baseline, and at B it is minus Wx square by 2, so it is a parabolic variation. So whenever it is given with the uniformly distributed load, the bending moment variation is parabolic. Thank you for watching. Please like, share and subscribe the video. Thank you.